This property is useful, and again, this is just another way of thinking about this, because if I could figure out the right power to apply to both sides, because if I square both sides, then as long as I do it to both sides, I'm okay. So for example, if 10 equals 10, then you can probably agree that 10 squared equals 10 squared. So as long as I do the same thing to both sides, I should be fine. Well, what I really want to do is get rid of an exponent of 7. So, because I know that if I raise this whole thing to a power, I can multiply. Well, what do I need to multiply 7 by in order to cancel it out? Because, really, I want to solve for x to the first power. Well, if I raise both sides to the 1/7 power, what does that do? Well, 7 1/7 is equal to 1 whole. Therefore, I would just end up with x to the first equals, and in my calculator, I could do 15 raised to the 1/7 power. So let me go back here and type this in. 15, let me put this in parentheses, 15 raised to the, 15 raised to the 1 divided by 7. I'm putting that fraction in parentheses. And I get x is about 1.47. Now, how is that different than if I just took x to the 7th equals 15 and took the 7th root of both sides? Which, by the way, only one answer. It can only be positive because I have an odd number of multiples. So if I took the 7th math root of 15, notice that we get 1.47 as well. I prefer this method because it just is a little more convenient. So what about y to the 2.7, or let's even do negative 2.7 equals 12. Okay, well, in order to figure this out, I have to cancel out the negative 2.7. So what am I going to raise both sides to? I'm going to raise it to 1 over negative 2.7. Because negative 2.7 times 1 is negative 2.7, divided by negative 2.7 is 1. So if I do the same thing to both sides, I should be okay. So those will cancel and leave me with y to the first equals 12 raised to the 1 divided by negative 2.7, excuse me. And I get, voila, an answer of about 0.398. So that means 0.398 raised to the negative 2.7 power gives me 12. And that's a way we could, something that we'll end up using in order to be able to solve for situations involving exponential functions. Let's now mention division of bases. So what if I have 3 to the 5th divided by 3 to the 3rd? Well, what does that mean? Let's just write out our definition of 3 to the 5th. And let's write down our definition of 3 to the 3rd. Well, if I wanted to simplify this, of course I could just plug this into my calculator and figure out what it's going to become. But I can actually simplify the amount of entering I need to do on the basis of, well, I really have 3 divided by 3, 3 divided by 3, 3 divided by 3, 3 divided by 1, and 3 divided by 1. And so what that allows me to do is, if I divide by 3 3 times, and I multiply by 3 3 times, then I basically undone everything, and I just end up with 3 squared over 1, or more simply, 3 to the 2nd power. So what really happened here? Well, conceptually, we just canceled out the like things in the numerator and denominator that were being multiplied. But notice that really what ended up happening with the exponents is they ended up being subtracted. So 3 to the 5th over 3 to the 3rd is equal to 3 to the 2nd power, which is the same as 3 to the 5 minus 3. But what if we reverse that? How would this look now? Well, very similar, except that every role would be reversed. So now I wouldn't cancel out 3 multiples on and have 2 multiples left on the bottom. I'd have 2 multiples of 3 left in the denominator. So what would I have? Well, really, you can always multiply by 1. So the multiplication by 3 and division by 3 cancels out, and I'm left with 1 over 3 squared, which is equal to 1/9. But also notice that if I use the subtraction rule, 3 minus 5 is negative 2.